maybe we can start, and then if people trickle in afterwards, it doesn't really matter.
All right.
Cool. Yeah. So welcome everybody. And it's a pleasure to have Adam Block today. He's a PhD student at MIT. I guess you're Sasha student officially, or not? Okay, Sasha student. So he's going to talk to us about some really exciting stuff on generative modeling via score function matching and Langevin and sampling using Langevin dynamics. So take it
All
away.
right. Hi, guys. Thank you so much, Andre, for inviting me. So I'm going to talk about some recent work that I did with my advisor, Sasha Racklin, and a collaborator over at IBM, Youssef Mrua, where basically the problem that we're looking at is that you're given x1 through xn IID from some distribution P, and you want to generate a sample x hat such that the law of x hat needs to be close to the law of P. And so the closeness that we're going to be talking about is the Wasserstein distance. So just in case anyone needs a refresher, we have that if mu and nu are laws on RD with finite second moments, then we define W2 of mu nu as the infimum of all couplings gamma of the expected x minus y squared, where x, y are according to gamma and the marginals are according to mu and nu. I think this is pretty standard. And so overall, like what we were actually looking at is image generation. And so there are kind of two problems here. So the first problem is learning P. And also, if you guys have any questions or want me to write more clearly or something, just interrupt. Okay, and so the second thing that we need to do is that given an estimate, we need to actually sample efficiently. And so I'm going to spend a little bit of time talking about each one of these, but I'm actually going to focus on the sampling efficiently, because I think that the main point of this work is that we're going to be talking about Langevin sampling, and lots of people run Langevin sampling in practice with kind of estimates of the score. And while there's a lot of work that shows that like if these estimates are uniformly close to what the actual score of the distribution is, then like this scheme actually works. There aren't really, to our knowledge before this, any estimate, any like concrete theoretical reasons why if you only have like L2 closeness for your estimates for the Langevin dynamics to actually still work out. And obviously this is important because generally we only have theoretical guarantees of like squared error being small rather than any kind of uniform closeness guarantee. So without further ado, we're going to go into the part one, which is learning P. So we're going to restrict P is on RD, and we're just going to pick some notation. So let G sigma squared be the density of an n of 0 sigma squared I. And then we're going to define P sigma squared to be equal to P star G sigma squared. And this will quickly become important. And so the part of P that we actually need to learn about is something called the score. So we define the score of P is del log P. And obviously there are some questions about existence and regularity. So for instance, if P is only supported on some subset of RD, then obviously we don't have a density. Like this is just infinite away. And then you can ask like, what if P isn't regular enough for this to be defined? But we're only going to be working with the score of the smooth distribution anyhow, so we're going to ignore any of those considerations. And so the way that we're going to estimate the score is we're going to be using a denoising autoencoder. And so we have to define two losses. So we're going to say that we're going to let R and S be vector fields on RD. And we define two losses. So let's call LDSM for denoising score matching of S is equal to E of X according to P sigma squared of just the squared error. And then we're going to define the denoising autoencoder loss as E of X according to P now, and C according to G sigma squared of R of X plus C minus X squared. So what's going on here? So the first one, it seems pretty straightforward. We're just training something to approximate the score, but notice that it's the score of P sigma squared, and this is first of all supported on all of RD, and second of all, it's always smooth, so this is always well defined. For the second one, what we're doing is we take a data input, we corrupt it with a little bit of Gaussian noise, and then we try and recover what our original data input is. And so maybe it's not entirely clear why these are related. I believe the first relation was noticed by this guy Pascal Vincent in like 2008, and then Elaine and Bengio wrote a kind of a paper that examined kind of asymptotically as the amount of noise is going to zero, how this interacts with the score. But we actually have kind of a non-asymptotic version, which is that we can actually relate these two losses, and in fact they're actually equivalent up to kind of an affine transformation. And so what I mean by that is that let's let SR of X equal R of X minus X over sigma squared. Then LDAE of R is equal to LDSM of SR plus a constant that doesn't depend on R or S. And this is, I mean, these optimization things are equivalent. And so we kind of get as an immediate corollary that if R star minimizes the DAE loss, then R star of X is equal to X plus sigma squared del log P sigma squared of X. And so the proof of this proposition here is essentially just the divergence theorem and the Gaussian sign identity, and you kind of compute that. So I'm not going to show that here. It's available in our paper that's on the archive. The corollary then obviously follows immediately, just because it's quite clear what function minimizes the DSM score. So maybe some quick intuition as to why this holds is that, like, we can think of this as from a Bayesian standpoint, is that if we're only given the corrupted data point and we already know P, then like the corrupted data point minus the noise, like kind of our posterior, right, should be stepping in the direction that kind of maximally increases the probability that we had this data point that we observed. And so you'll note that del log P sigma squared points in the same direction as del P sigma squared, and so everything else is just kind of normalizing factors. So maybe it's not so surprising that we get this. But this is all well and good, but like in practice, we want some finite sample bounds. So we have some finite sample bounds, which we will. So we're going to let F be a class of functions or vector fields. And so we're going to want F to be in r times infinity ball. So this is the image of all the f's, coordinate wise, they have to be bounded by r. And then we also want like f is rich enough such that inf of e of f of x minus del log p sigma squared is 0. So this is a well-specified case. I mean, obviously, this is kind of standard stuff. So what do we have? We have, let's let r hat be in the empirical minimizer of the DAE loss. So so maybe this is for f and f of x plus ci psi squared. And then we have some nice high probability bounds, which says that with probability greater than or equal to 1 minus delta minus like cn r to the minus r squared over m squared, where p is 1 over m sub Gaussian, we have that e of r hat of x minus x over sigma squared minus the actual score is, sorry, maybe I'll do this down here. It's O of 1 over sigma to the 4th times the Rademacher complexity of that. So this may be a lot to take in, but all I'm saying is that we have this nice high probability bound. Oh no, maybe I should include an r squared here to see how what the dependence is. All I'm saying is that we have a nice high probability bound on what the squared error is of this guy over here, which is our estimate of the score and the actual score. And so I should continue to stress that this is, I mean, first of all, this is pretty general, right? Because this is true for general function class. In practice, you actually use some kind of class of neural networks and optimize, and you get pretty good results. The other thing I should probably note is that we are, this kind of f being rich enough, we're kind of in the interpolation regime, but in reality, when these kinds of things are being fit, you don't actually want to be in the interpolating regime because it's too complicated, it's too rich. But in practice, you actually do get pretty good fits for this. So this is maybe some like a minor remark. And I'm not going to give the proof, it's just empirical processes. And that's not really what this talk is about. So we're not going to cover that. So now with this kind of quick introduction, I just wanted to briefly glance over those results because what I really want to talk about is now, you know, we have an estimate of the score and we have to figure out what to do with it. And so that brings us to our second section.
Hey Adam, before you switch gears for a second, so the Song and Hermon paper doesn't actually fit the autoencoder objective, right? Like, so they rewrite
Yes.
the DSM objective in some way that just involves, I guess the way that it's written, you can't actually fit it because you need like log p of x, which you don't have. And so they rewrite it in some other fashion, right?
Yeah, so score matching was, especially denoising score matching, I think was invented by Hyvarinen. And so, yeah, you don't actually have del log p sigma squared. And so you can do, again, using the divergence theorem, you can transform this objective into something that's actually, you can actually work with. And that's what they do. And then the other thing computationally that they do is that they actually train, like instead of training, we're going to be talking about annealing. So like this is dependent on the noise level here, the sigma squared. And so instead of training like a bunch of different score estimators, they essentially kind of train them in a group, just adding this this noise parameter as like an extra parameter for their data. And this is partly what they find so effective. But yeah, I mean, like to me, I think that the DAE and the DSM are equivalent, and I think that the empirical processes for like the DSM and for the DAE is well tractable, because we're assuming like, what they call is that they have these like noise conditional score networks, which is much more complicated because there are complicated dependencies within the data. So this is maybe a little bit more mathematically tractable, but again, it's the same loss, so you can go between these things. And also maybe one more point to make when you're actually training this is I think that the DSM is a little bit more numerically stable, because eventually you want to have like somewhat small noise thresholds, and subtract, like taking R of X and then like the recoder and then subtracting off X and dividing by sigma squared might not be the most stable. But I'm in math, so this kind of thing doesn't matter as much to me. Good question. Does anyone else have any questions before I switch gears? Okay, so now we're going to be talking about the Langevin sampling. So for those that do not know what Langevin sampling is, I'll give a quick introduction. So we have the score, or an estimator of the score. And so what we want to do is we want some MCMC method that like gives us an actual sample. And so the method will be as follows. So let f hat be an estimate of the score. And then so we initialize x naught according to some maybe new naught, and let x I plus 1 is equal to x I plus f hat of xi times eta plus root 2 eta xi, where xi are standard normals and independent. And so the idea, this is clearly an MCMC method, and the hope is that the law converges to something close to being the law of the original distribution. And why might this be motivated? Well, we can consider the following like a diffusion process, which is dxt hat is equal to del log, oops, I'm getting ahead of myself, is equal to f hat of xt hat dt plus root 2 dbt. And so now this is maybe this kind of would motivate us to consider the following Ito diffusion. Dxt is equal to del log p sigma squared of xt dt plus root 2 dbt, which is the Langevin diffusion. And so under pretty weak conditions, this guy is going to converge in law. And so let's just fix some notation here. So let the laws of xt hat and xt be nu t hat and nu t. And so, I mean, at least it's intuitively clear that this discrete xi plus 1 is kind of a discrete approximation of this dxt hat, and maybe we hope that this dxt hat is pretty close to this dxt, and then if we run t for long enough, then we hope that, well, we know that nu t converges in distribution to p sigma squared, and so like this gives us some hope as to how to sample. Obviously, there are a few issues here, especially with actually quantifying the rate at which these things converge, and kind of that's what we'll be talking about. So first of all, we might need some conditions. So we're first going to assume So one is that del log p sigma squared and f hat are m over 2 Lipschitz. I can never remember if there's a c there. And then the second one, so this is pretty standard, and the reason that we need Lipschitzness is that we need it for several reasons, but first of all, it guarantees the existence and uniqueness of these diffusions for infinite time. So that's useful. Number two is we need that minus del log p sigma squared is MB dissipative. And this is maybe is a little less standard. And what this just means is that for all x, so there exists m greater than 0, such that for all x, minus del log p sigma squared of x with x itself is greater than or equal to mx squared minus b. And so this is maybe a little less standard. You can think of this as a very strong, well, very weak version of convexity. It's actually weaker than being convex outside of some compact set, but it does ensure fast mixing in some sense of the Markov chain, which we'll get to in a second. So, and these are really the only two assumptions. And actually, this is kind of relevant because if we don't assume anything more on this function class, right, then it makes it maybe somewhat difficult to analyze this xt hat. And so we're kind of forced to compare xt hat to xt. And I'll get to that a little bit more in a minute. So I'm just going to state the theorem that we're going to spend some time on. And it's going to look a little ugly. So assume 1 and 2 above, and let E of p sigma squared of f hat of x minus del log p sigma squared of x squared is less than or equal to some epsilon squared. And we're also going to assume that the dimension d is greater than or equal to 3. And so we're going to let mu k be the law of xk, where xk is just the kth iterate of this guy up here. And so we have that w2 of mu k p is bounded by sigma root d plus some constant times root d eta tau e to the m squared over 2 tau, where we're going to set tau equal to k eta plus w2 of mu naught p sigma squared e to the minus 2 tau over CLS, and I'll get to all of this notation in a second, plus the particularly ugly term, which is root d tau times epsilon tau plus e to the m root d tau times root tau times epsilon to the 1 over d, also the 1/4. And so you may ask why I include all of these ugly terms. And so maybe I should break some of this down. Sorry, this might not be super legible. Okay, so first of all, this CLS we're going to get to in a second, but it's just a constant. And so what we notice is that tau is equal to k eta, it's kind of the time parameter. And so if we run tau for a large time, then this term and this term are going up exponentially, actually, here, but this term is going down exponentially. So maybe there's some kind of sweet spot that is exactly the amount of time that we should run this Langevin diffusion. And I'm going to get to that when we talk about homotopian annealing near the end of the talk. But let's just keep that in mind. So where do all these ugly terms come from? Well, like this is actually the term that we're going to spend the time on. I think this is the most interesting one, but let's just kind of break down where this comes from. So first of all, W2 is just is a metric. So we have that W2 of mu k p is bounded by, so there are 4 terms and each one corresponds to a different probability law. So we have W2 of p and p sigma squared plus W2 of p sigma squared and nu infinity plus W2 of nu infinity nu t. Sorry. Well, yes. Plus W2 of nu t hat. Then finally, plus W2 of nu t hat mu k. So what do we note immediately? Well, this term, we already decided that nu infinity and p sigma squared were the same, so this goes away. What else do we note? Well, this term is going to be very easy to handle. I'll say more.
Adam, sorry, a quick question. What was nu infinity again? I kind of lost track a little bit of the notation.
Oh, sorry,
nu infinity?
sorry. So nu t is the law of xt, the Langevin process. And since the Langevin process converges in distribution, nu infinity is just the law of is just the limit
gotcha.
of the nu t's.
Gotcha.
Sorry,
and the hat is the discretized version. Okay.
And so no, the mu is the discretized version. The hat is the estimated diffusion.
Gotcha. Okay.
So the way to envision this is that we have kind of 2 diffusions running, and each diffusion is like one. The idea is that hopefully they're pretty close to each other, because one is run by, like, the drift is given by the estimate of the score, and one is given by the actual score. And so maybe before I go any further, a natural question to ask is, why do we do this? Like, this is certainly one breakdown that's legitimate, but what if we, instead of doing this, we try and say, like, okay, let's look at nu hat infinity, nu hat t, and then look at the difference between nu hat infinity and p sigma squared. And then we could kind of get rid of these 2 diffusions. We really just have one diffusion that's converging, and then we want to look at its stationary distribution and consider its W2 from the stationary distribution to this p sigma squared. And the thing is that that doesn't really work, because in our generality, it's not clear that f hat is actually the gradient of like the potential of a Gibbs distribution that has finite measure, and so it's not even clear that, like, W2 of nu hat infinity and p sigma squared is even finite. And then moreover, like, even were it finite, then this kind of convergence, which we'll see comes from the finiteness and boundedness of the log Sobolev constant, is not guaranteed, because there just isn't enough structure on the f hat. Which actually kind of motivates an interesting question of, like, what kind of realistic structure could you put on the function class f hat for your estimators, so that so that you actually have some good bounds on this, and, like, maybe it would mix much more quickly. And that is actually something that we don't really have a good handle on, because it's kind of difficult to enforce various kinds of disputivity for neural networks and stuff like that. So is everyone clear on the breakdown? We basically just introduced a bunch of different intermediate laws and bound their Wasserstein distances. So now maybe we should just kind of quickly go past the easy ones. So this one is the error that's due to the discretization. That's kind of the difference between the law of this xt hat and the law of this xi plus 1. And I'm not going to focus on that. That's pretty standard. And also, I think it should be noted that, like, if you run maybe a better discretization, like a stochastic Runge-Kutta, you can reduce this by some reasonable amount. But so we're going to actually ignore this term. This term is very easy, because we have the following lemma with a 1-line proof that W2 of p sigma squared p is less than or equal to sigma root d, and the proof is consider the coupling of x and x plus c, where x has distribution p and c has distribution g sigma squared, then it's clear that the variance of g sigma squared, the standard deviation is just sigma root d, so this suffices. So now I said, so we've taken care of this. This is done. We are ignoring this, and this term is 0, this second term. So now we have 2 terms to look at. So let's talk about the easier term first, which is the convergence to infinity. So I'm not sure how much detail you want me to really go into in terms of log Sobolev inequalities and log Sobolev constants, but I guess I'll just say that if p sigma squared satisfies a log Sobolev inequality, then, with constant CLS, then W2 of nu t p sigma squared is less than or equal to W2 of nu 0 p sigma squared e to the minus 2t over CLS. So we have exponential decay in the Wasserstein distance. And the key point is that we kind of need to bound this log Sobolev constant, and I can go into more detail if you want, but I don't really want to spend a huge amount of time on that. But the key point that was noted, I think someone figured this out, like the relation between distributivity and log Sobolev constant bounds. I think it comes from a paper by Cacheux and some other people. But basically, you have the proposition that if minus del log p sigma squared is m over 2 Lipschitz and mb dissipative, then CLS is less than is O of m over m d squared e to the 8 m over md. And so it may not look so good because we have this exponential dependence in dimension here, but note that if we did not have an exponential dependence in dimension without any further assumptions, this would give a fast way to do non-convex optimization, which is NP hard. And so, functionally at least, we kind of need this dimensional dependence in here. It's true that if we assume more about kind of the score, del log p sigma squared, then we can get better dependencies. Like obviously there's a classical Bakry-Emery criterion that says if it's convex, so, strongly convex, then we get a nice dimensionally independent version. I can speak kind of at the end. Some of our recent work that we're doing right now is, you make some assumptions on like the manifold hypothesis, and you can get much better rates. But this is what we have right now. And so in particular, we with this level of generality, it's not really realistic to expect that you have better mixing time than exponential in dimension because of the NP hardness of non-convex optimization. So that really probably cannot be improved, unfortunately, without further assumptions. And so now we kind of have taken care of 3 of the terms rather quickly. So let me know if you have any questions. If not, let's move on to this last term, which I think is kind of the most important. And a little bit of history is that Dalalyan and Saibakov, and then Dalalyan by himself kind of gave this series of papers where they apply this technique of, they control the KL divergence between these 2 laws, and they do this using Gersanov. And this assumption is made on kind of a uniform distance, a uniform bound between the score estimator, wherever f hat is, kind of a uniform bound instead of this L2 bound. And so what we're going to do is we're going to kind of generalize this to the L2 bound using some of their techniques and some of our techniques. So we want to focus on, let's just make this its own section, W2 of nu t and nu t hat. So the steps, kind of the broad outline. So one is we'll reduce to controlling KL. Two, we'll use Gersonov to bound KL. Then three is we'll use geometry to conclude. So as I say, these steps are standard. The step is novel. Okay, so first of all, let's just kind of quickly run through these standard things. So we have this nice theorem of Bali and Villani that states that suppose x according to nu t such that we have some kind of exponential integrability, alpha xt squared is finite. Then there exists C alpha finite such that W2 of nu t of mu nu t, where mu is any distribution that's absolutely continuous with respect to nu t, that's controlled by some C alpha times KL of mu nu t to the 1/4. Oh, I'm running out of space. Let me move this down there. Okay, plus KL of mu nu t to the 1/2. And in particular, since we want these things to go to 0, what we really care about is this 1/4 term. But the important thing is that all we need to do is bound the KL of mu nu t. And so obviously we want to apply this for mu equals nu t hat. And so first of all, we need, I guess, to show that this exponential integrability statement, we can get nice bounds on both of these using kind of the Lipschitzness and some, not so very difficult stochastic calculus. So I'm going to go past that because I don't think that's super important. But I hope you agree that we've effectively reduced this problem to bounding the KL of nu t hat and nu t. And then I have another proposition that I think is, it's just used Gersonov's theorem, and it was this technique, as I say, was pioneered by Delalyan, that says that KL of nu t hat, nu t, is equal, maybe I'll say equal to 1/4 times e of integral from 0 to t of f hat of xs minus del log p sigma squared of xs squared ds. And so where does this come from? Gersonov. So if you remember Gersonov's theorem, it just says that we can, by changing the measure, we're changing the drift, and it gives us exactly what the Radon-Nikodym derivative is, and all you have to do is you have to, use some regularity, which we can establish without too much difficulty, and then your Radon-Nikodym derivative, the logarithm of it, has a martingale part, and it has the quadratic variation part. when you take expectations, the martingale part drops out, and so you're left with this expression. And so again, these computations are pretty standard, so I don't need to spend a huge amount of time on them. And so now we can move forward a little bit to bounding this. And here's the point where if f hat and del log p sigma squared are uniformly close, then we are done. And that's because it's obvious that if we have this kind of uniform closeness, then we have this expectation is small, and we're done. But the problem is that we know that this L2 is small, but we know that L2 with respect to p sigma squared rather than L2 with respect to nu s or nu t or anything. So we really don't have like a huge amount of control on this quantity here. And so here's where we're going to need to use some of the geometry. And so let's just give kind of a quick sketch of the proof. So first of all, let's just for notational sake, let's let phi of x equals del log p sigma squared, or f hat of x minus del log p sigma squared of x squared. And so we can think, you know, like maybe this isn't uniformly close, but it's has to be like pretty small on like a reasonably large set. And so we let U to be equal to the set where phi is greater than epsilon. So U is kind of the bad set where phi is far apart. And we also have the good set. And so we can just break this integral, which we need to control, into the good set and the bad set. So we have, okay, so we have that E of integral from 0 to t of phi of xs ds is, certainly we can break it into E of integral from 0 to t of phi of xs 1 u complement ds of xs plus E of integral from 0 to t of phi of xs 1 u of xs ds. And so this first term, well, this is just bounded by epsilon t, because on u, obviously phi is less than or equal to epsilon, and so this is just less than or equal to epsilon t. So the thing that we really need to bound is the second term. So how do we control the second term? Well, we can kind of naively apply Cauchy-Schwarz, because what we really want to do here is that we know that we can control this phi, this moment of phi, as I'll show, but the thing that we really want to control is how much time does xs or does x actually spend in this bad set u. So we notice that maybe I'll just copy it and bring it down. Okay. Oops, we have some stuff that we don't want. So this is less than or equal to, just by Cauchy-Schwarz, epsilon of integral from 0 to t of phi of xt squared of xs squared ds times E integral from 0 to t of 1 u of xs ds. So, okay. So let's track each of these factors, and stop me if this is getting a little confusing, because I know that we're going through lots of terms here. But so now this first factor here, we can bound, and the reason is that we notice that we assume that f hat is Lipschitz, And del log p sigma squared is also Lipschitz, so we can actually contain the growth of phi with respect to x. And so what we have in particular that phi of x is less than or equal to m to the fourth times x to the fourth plus b to the fourth for like b, say the norm of the score at 0. And okay, so what does this tell us? Well, we can use some distributivity and some Gronwall and some kind of standard tricks to bound like e of xt to the fourth is less than or equal to some stuff. And once again, the computation is in the paper, but I don't think I really need to go into that here. So this is controlled. So what we really want to control is this guy over here. And so we notice that e of integral from 0 to t of the amount of time that you spend in a set is equal to the integral from 0 to t of the integral over u of pi s, let's say we're starting at some point x, pi s of x, y, dy, ds, where pi s is the transition density. So this is just by kind of the basic theory of Markov processes and diffusions is that, what we really care about is the amount of time that we're spending in this bad set. And so we can say, okay, we have this transition density. How can we control that? Well, we can again use Gerstenov to bound the transition density kind of with respect to a Gaussian. And so we have that pi t of xy is less than or equal to p sigma squared of y over p sigma squared of x of e to the m root d over 2t gt of xy, where this is just the solution to the heat equation, is just the Gaussian with variance t. And so what do we have here? Well, first of all, we don't like this term here because we see that it's growing with the dimension. But I should mention that this is only due to the fact that like our bounds are just assuming Lipschitzness. If we assume greater regularity for del log p sigma squared, we can get this to be constant in dimension, and we just have to bound the Laplacian of the log likelihood. So we don't actually care that much about this. And actually, I should note that in like PDEs, there's been kind of a long history of people trying to bound these transition densities because these are the solutions to uniformly hyperbolic equation or parabolic equations, and for some reason the analysts care a lot about this. But this bound in particular does not make use of any kind of boundedness assumptions on the drift of our diffusion, which is kind of important because obviously we don't expect the score to be bounded. Okay, so we have this bound. Where were we? Well, we were still trying to bound this occupation time. And so we notice that the integral, so we have that the integral of u of the integral from 0 to t of pi s of xy ds dy, well, it's less than or equal to what we just found. So I'm just going to pull the relevant factors outside, m root d over 2t over p sigma squared of x times the integral from u, integral from 0 to t of p sigma squared of y, gs of xy, ds dy, where again, we just kind of substitute this bound in. So what's the key point here? Well, we're just going to bound, this is actually where we use the fact that dimension has to be greater than or equal to 3. And I actually think that this is not really a loosening of the bound because we're just going to bound this. I'm just going to copy and paste this exact thing. Okay. And we're going to replace the t with an infinity. So This is the technical point because Brownian motion is recurrent in dimension 2 and in dimension 1, but is transient in dimension 3. So if we take t to infinity, then this integral remains finite. And I think that this is actually not like a super bad like weakening of the bound. Like it might seem like the bound should be really weak by taking from t to to infinity, but I think it's important to note that the graph of kind of gs of xy for fixed x and y looks kind of like this. And this peak is both very, very narrow, and it kind of goes to a needle, as d gets big. And what happens is that this is essentially 0, everything after the needle. And so we expect that in order to be mixing, we're going to have to be moving past this needle. And so like the integral, like if we end up stopping our algorithm at like this point right here, then the amount of extra mass that we're accruing over out to infinity is probably not so much. So I don't think that this is in general that big of a weakening of the bound. But with that remark aside, we notice that this is root d over 2 over p sigma squared of x, integral of u, and then we actually can just integrate this out, and we get that this is gamma of d over 2 minus 1 over 2 pi to the d over 2 times x minus y to the 2 minus d p sigma squared of y dy. And so this gamma to the gamma of d over 2 minus 1 factor might scare us, but we'll see that this actually is going to kind of magically get canceled out later on in the bounds. And so we can actually move that outside of the integral. And we're kind of left with, so now if I can just sum up what we've just done, so we just need to control integral of u of x minus y to the 2 minus d p sigma squared of y dy. And again, we don't really have that much control on what u is, besides that we know what p sigma squared of u is bounded by, just by kind of a Markov inequality. It must be like bounded by epsilon. So in order to bound this, we have to kind of think of like a worst case u. And the worst case u, you might think is just kind of a ball around x of a certain radius, because that's when this first factor here gets like really, really, really big. And so you'd actually be right that this is the worst case, but it's not, maybe it's not like super obvious that this is true, because we have this kind of weighting factor of p sigma squared of y. So you might be worried like, okay, what if we kind of, instead of choosing a ball, we could choose this to be like really, really small, but this were, gave it more mass or something like that. And so, it's not completely obvious. And in order to prove, in fact, that this is the worst case, we're going to use some geometry. And so I don't know if people know about like symmetric decreasing rearrangements, but we're going to use kind of a slight generalization of this, which is related to isoperimetry. So let's kind of just define, let mu be a probability measure on RD, and let H maybe take RD to the non-negatives. And so we can define mu f of S to be equal to the size of the superlevel set. And so obviously this is decreasing in S. And so then we define the rearrangement, the decreasing rearrangement. Oh, this is an F, I'm using an H. Sorry. Okay, then we define the decreasing rearrangement, H star of T, as defined as the inf of the set of S greater than 0, such that mu H of S is less or equal to T. So this is maybe a little bit confusing, So what are we really doing? Well, maybe the easiest thing to think about, and this will actually be relevant because this is kind of the case that we'll apply it on, is just kind of indicator functions. So like if we let mu, so we don't actually need it to be a probability measure, we can just assume that it's sigma finite. So let mu just be Lebesgue, and h equal 1a for some measurable set a and Rd of, say, finite volume. So what we get is that we end up getting that h star is essentially equal to, of t is equal to the indicator function of like t being less than the volume of A. But the more maybe geometric way of thinking about this is if we look at this mu h of s, we end up getting kind of we change this into a set that is just a ball around the origin with the same volume as this original set A. And again, like people from PDEs actually use this a fair amount. It has a lot of connections with isoperimetry. In fact, what we are going to be using, which is the Hardy-Littlewood inequality, is kind of a generalization of the isoperimetric inequality. Maybe this example is not so enlightening, but to me, I think of the symmetric decreasing rearrangement is the way to really think about these rearrangements. But so why is this relevant to us? Well, there's kind of a famous theorem of Hardy and Littlewood and so what does it say? Well, it says that the integral of Rd of, let's say, h1 of x, h2 of x, d mu of x is less than or equal to the integral from 0 to t of 0 to infinity of h1 star of t, h2 star of t dt. And so again, maybe this is kind of surprising, but I claim that this is really just a generalization, kind of a functional generalization of the isoperimetric inequality, because if you take mu equals the Lebesgue measure, and you take maybe like one of these constant and the other one equal to the indicator of a set, then all we're saying is that we can kind of relate the volume with the perimeter using these, and we essentially, the isoperimetric inequality pops out, and we say that the ball is really kind of the optimal guy there. And in our situation, we can actually still apply this Hardy-Littlewood, where are we, with these functions, this x minus y to the 2 minus d and mu, and u. So let h1 of x equal just the indicator of this set u, and h2 of x equal, sorry, I guess maybe we should be using y here. So h2 of y is going to be this x minus y to the 2 minus d. And so we can just literally plug this into the Hardy-Littlewood theorem. And I mean, I'm not going to actually do the calculations here because maybe they're a little bit irritating. But the point is that this says exactly that the worst case set for what u can be in this right here is that u is this ball around x of a given radius. So now maybe we can just plug this in, and again, I'm not going to do the calculations, but we have that u of x minus y to the 2 minus d of p sigma squared of y dy. Oh yes, I hope that it is obvious, but if not, then we're setting mu equal to p sigma squared in this case. So this is going to just be less than or equal to omega d to the 1 minus 2 over d times p infinity to the 1 minus 2 over d times d over 2 times p sigma squared of u to the 2 over d, where omega d is the volume of the unit 1 ball and p infinity is just its maximum. So the p infinity is, we're going to kind of ignore for now. But this omega d to the 1 is actually quite important because you may remember that omega d is equal to something like 2 is like pi to the d over 2 over gamma of d over 2 times like some poly and d. I can't remember the exact, something like that. And so this is very, very small, but you remember that in order to get here, we added in this factor of gamma of d over 2 minus 1 over pi to the d over 2. And so this exactly cancels with the omega d, and that factor entirely drops out. And unfortunately, what are we still left with? Well, we're still left with this p sigma squared of u to the 2 over d, which we actually can control now because we know that p sigma squared of u is less than or equal to epsilon. And so if we kind of plug this back into each of the steps that we've just done, what we see is that we have the bound that we got from the theorem. And so we're actually done with that. Now, what is this 2 over d doing here? And is this tight? And the answer is that, so we're not actually entirely sure if the dimensional dependence for W2 is tight. It's not that hard to show something kind of similar with a lower bound to show that in KL at least, that this is tight. You kind of almost do the exact same thing. You have to be a little more careful. Instead of doing a Cauchy-Schwarz, you do a reverse Holder. And then you just take as your set F, your function f, your estimate. You assume that the set where it's not very close to your score is given actually by this worst case set, and you can actually just compute this. And so this 2 over d does show up in KL, but as we know, like Wasserstein does not control KL, so lower bounds for Wasserstein are maybe a little harder in this case. And I actually think that it's interesting to wonder whether or not this is actually tight, or we can get dimension-independent bounds in Wasserstein distance between the laws of these two diffusions. And obviously, this is useful for application purposes. But so what does this motivate? Well, this motivates that we kind of want to be sampling in lower dimension, which I guess people already maybe know for computational reasons, but at least for this kind of approximation reason, this suggests that maybe we should be looking at that. And so but kind of just before I conclude, what I want to do is I want to talk about the thing that Song and Ermon actually did that made their algorithm so successful. And this is a paper that Andre had alluded to when he asked the question way back when. And this was, they were generating. Yeah.
Sorry, before you switch gears, so I guess I'm not entirely sure like what you were saying is tight or not. So suppose that F is maybe strongly convex or something. So you're trying to sample from a strongly log concave distribution. Do you still have to have the d dependence, or like, or do you know whether or not you have to have the d dependence?
Sorry, by tightness I mean, so in the worst case scenario, my AirPods are going out. So what I'm saying is that with these assumptions, there exists of functions like with score del log p sigma squared and the score estimator f hat, such that this d dependence shows up in KL. Obviously, like you can definitely, if you have convex, like if you assume more things about either f hat or del log p sigma squared, well, especially about f hat, you can definitely speed this up. As I say, like if you assume that f hat is, say, convex, then the analysis I think changes a little bit, because what you can do, or I guess f hat should be concave, but the analysis changes because remember how we broke down long time ago, we broke down the error into these 4 terms, and I mentioned that maybe this isn't the natural way to break the error down. Like, what if instead of this we chose like p sigma squared we kept, but instead we didn't examine like 2 diffusions. We only examined the diffusion of the estimate and wondered like how long does it take to mix, and then once we have that, like how far is this stationary distribution from p sigma squared. And so yeah, with further assumptions, I think you can actually get much stronger bounds. And so, for instance, it's actually.
Oh, sorry. So I guess I'm asking something just like for the bit that you were doing. So suppose that you just take the current, I guess, like a high level approach, and you're still trying to
Hmm.
bound W2 of nu t and nu t hat. But suppose that you, instead of the distributivity condition, you know that the distribution is strongly log concave, or maybe even Gaussian, let's just say. I'm trying to figure out like whether the exponential indeed that you're losing is somehow like a consequence of the fact that you want something weaker, so you want something this like dissipativity conditions, or whether like if you have something just like strong convexity or something, whether
So,
you still have to have that D.
oh, I see. So with this, it has more to do about like it's not just a condition on f hat, it's a condition on p sigma squared as well. Because what really matters, so what really matters is how much time you're spending in
Right,
like
right.
a bad set, right? And so I think, you know, if if you can control the bad set, then you can control how much time you're spending there. But like the you know, even if f is say convex and maybe del log p sigma squared is maybe convex, like the point is I'm sure that you could come up with like a function. I think you could come up with a function where like they're very close. Maybe I'll draw it down here. Like these functions are very close. uh, that's one function, and like this is the other function. See, they're very close, but they're very far on this ball. And the problem is that if they're very far on this ball, and this ball just happens to have a lot of mass with respect to p sigma squared, then you're going to be in trouble, right? Because you're still going to, the diffusions are going to be spending a lot of time here, right? Oops, I don't know what happened there. But so the diffusions are going to be spending a lot of time here if there's like the path of diffusion. And what we would kind of like it is if the diffusion were to be maybe going in here, but spending much more time out here, right? I don't think that a convexity or anything will necessarily help with this.
Cool. Yeah,
And it
that's what I
actually
was wondering.
has, yeah, and it has more to do with the like the actual estimation stuff itself. Like that's a good question. Okay. Does anyone else have any questions before I move on to the kind of homotopy annealing step? So now, I can't remember what section we're on, but homotopy. So, okay, we noted that we have these kinds of four terms. We have W2 of p sigma squared. We have W2 of p sigma squared nu t, nu t hat, and finally, let's see if I can fit this in, nu t hat and mu tau. So, and let's just remember this is, oh, no. Okay, so this term is because p sigma squared and p are not quite the same. This term is lack of convergence of the stationary distribution. These are the two different diffusions, and this is the discretization error. And so you can ask, like, given some set of parameters, like how long do you want to evolve your Langevin diffusion? And we notice that like these terms, so if we are evolving it for a while, this term just doesn't change. Okay, this term, these terms get worse, and let's choose maybe blue for things that are good. And so this term gets better. And so there's kind of a sweet spot for how you want to be optimizing this. And then the other question I guess you could ask is, what's the impact of this sigma squared on the rest of this? And so I think that the biggest impact that you can see is like maybe it has a small impact on the log Sobolev constant. I can actually speak a little bit more about that if we assume some more structure on P. But I think the biggest for sigma squared is that sigma squared smaller makes estimation harder. And I think that intuitively this should kind of make sense, because otherwise we should just send sigma squared to 0, and you know it doesn't really mean anything. so like there should be some kind of trade-off. And where we see that is actually in this bound way, way, way at the beginning in the empirical processes bound, is that you see that you get this this over sigma to the fourth. So with sigma squared going down, this squared error term is getting much, much larger. And so you need many, many more samples to do this. And remember, so what is this term controlling with high probability? It's controlling the epsilon that we saw in the theorem here, right? So, you know, these are the two parameters that we kind of have control over along with the step length, right? And so what Song and Aramon did to generate pretty high quality images for MCMC methods is that they said, like, why don't we just, why do we have to choose one? Why don't we just do a bunch of warm restarts and just anneal it? So they had this algorithm where you can, I need to switch my Apple AirPods, sorry. Okay, so what they did is that they said, okay, so take some pairs, say sigma 1, eta 1, all the way to sigma L, eta L, where sigma is the noise level. And remember that eta is the step length, or the step size for the discretization. And so, as I said, I don't really want to talk about the discretization. This isn't really super relevant. But obviously with smaller step sizes, you get better discrete approximations. But with larger step sizes, since we're analyzing this as kind of the time parameter tau is equal to the number of iterations k times the step size eta, with larger step sizes, we're evolving more. And so what Song and Aramon did is that they said, okay, so train score estimates S1 to SL, where SI estimates del log P sigma I squared. And then, so initialize like X0, run Langevin with like S1 and eta 1 to produce X hat 1, and then do a warm restart, and run Langevin with S2 eta 2 initialized at X hat 1, and then just keep iterating. So how does this help? Well, this allows us to kind of, or the algorithm to dynamically choose how far the Langevin should be evolved, and just kind of keep doing this. And so, you know, you need the Langevin to be evolved far enough so that it actually mixes, but you don't want it evolved too far that these other terms start dominating. And actually, empirically, you can see both actually Song and Aramon's work and some of the computations that my collaborator Youssef has done show that like you actually cannot evolve the Langevin for image generation too long, because you start getting these random stuff. And so what they do is that they they're able to take advantage of this, and it allows for dramatic speed ups. And so we can actually plug some of these estimates into our bounds, ugly as they are, and kind of heuristically, both from the bounds and what work in real life, you want like sigma I to be kind of proportional to eta I, and you want these to be decreasing. And so I would say that this is kind of the conclusion here is that like there's actually, you know, now firm theoretical foundation for why this particular kind of homotopian annealing step actually really helps, because we need to be early on accelerating the Langevin to be mixing as much as possible. And later on, we're kind of doing some less, you know, we don't need to mix quite as quickly, but we need to keep much more careful track, especially as this term later on, if sigma squared is getting smaller, then this last term, or this third to last term, this guy is going up by that what I said above. So I hope that this kind of gives you an idea of why the homotopian annealing actually works. So I think I can now take any questions if anyone has them.
Cool. Thanks, Adam. Yep. Please, somebody chime in with questions.
Oh yeah, I have a question. All right.
Mhm.
So yeah, can you repeat what you said? What happens when you run the Langevin too long? It just becomes noise, like it just totally loses the structure of the picture, or like.
Yes. So if like what empirically happens is that you run Langevin for kind of a little while, and the picture gets clearer and clearer, and then there's a point where it just kind of gets blurrier and blurrier and blurrier again. And I think that this actually suggests that in practice, once again, I keep going back to the fact that there are two ways to break down the error. One is that you're just looking at one diffusion, and then the other is that you're looking at these two diffusions. And I think that what this says is that with the kinds of functions that are actually used in practice, like these neural networks, you can't really look at just one of these diffusions, because then you should be able to mitigate this by just sending the step size down to 0 and evolving it for a while, because you should just be getting closer and closer to mixing. So I think that this does provide some empirical evidence to suggest that that's not really what's going on, and that you actually do need these kinds of two separate diffusions. Good question.
Cool. Guess that's it. Thanks, Adam. Yep.
Wonderful. Thanks for inviting me.
Of course. Thank you for coming. I'll see everybody else next week, I guess. See you guys.
Bye.